let us talk about infinity. Imagine opening your eyes and finding yourself surrounded by water, and you cannot remember ever not being in that water. The first question you might ask is,
how did I get here?
You've always been there.
What do you mean always? When did I enter the pool?
You never entered the pool. You have always been in the pool.
Okay, but where was I before I was in the pool?
That's a false question. There is no before in which you were not in the pool. You have always been in the pool.
Okay, but always, like, how long? Like, a billion years?
No, a billion years began a billion years ago.
Okay. But I must have been born at some point. What was before me?
Oh, okay, so, like, what's our communication disconnect here? There is no before you. You have always existed in the pool. Always. Forever. Infinitely.
Yeah, but
Always. Okay, so the point that I'm trying to make is that there are some concepts that we humans just cannot wrap our heads around. And one of them is the idea of something having always existed and having no beginning. We just can't really grasp that concept. It just doesn't compute. Like if I told you this road literally goes on forever, you'd be like, I don't get it, I cannot grasp infinity. Are we there yet?
nope.
Are we close?
Never getting there. Driving forever.
Here's another one. Try and imagine nothing. It's kind of impossible. At first, you might envision nothing as darkness. But darkness is something. It's darkness. So then you might say, is nothing just empty space? Well, empty space is something. It's empty space. But here's something interesting about nothingness. While we can't really grasp the concept of nothingness, we can describe it with mathematics. Roll film, please. Okay, don't panic. This won't be complicated, and I'll do it real quick. Can I get some background music? So there's this thing called set theory. And in set theory, everything inside a set is what exists. And if nothing exists in the set, then it is called an empty set. And that is basically a mathematical representation of nothingness. Or simply the number 0. It kind of represents nothing. I mean, the symbol 0 is itself a thing, but it can also represent a lack of things. So you can see how we can describe nothingness with math, even though we can't imagine it. Same with infinity. We can't grasp it, but we can represent it mathematically and use it to solve equations. So at least mathematically, infinity totally exists. So, why am I telling you all this? Because another one of the concepts that we have a lot of trouble grasping, even though mathematically it is not only describable, but actually well understood, is dimensions higher than the third dimension. So, you see the square? It has an x-axis and a y-axis. When it has height added to it, it becomes a three-dimensional cube. It basically grows a z-axis. Okay, that makes sense. A cube is a 3D version of a square. But here's some weirdness, my friends. Okay, listen carefully and just like flow with me. So, you can grow another axis to a 3D cube and get a 4-dimensional cube. Just like flow with me, flow with me. Now we can only perceive with our eyes and brains 3 dimensions, like this cube. So we can't really grasp this idea of a 4th dimension. It's like, huh? What the hell? 4 dimensions? Which is what you're thinking now. But while we can't really see or perceive a fourth-dimensional version of this cube, we can at least describe it mathematically. So just like this is a 2D representation of a 3D cube, here's a 2-dimensional representation of a 4D cube. There's also a 5D cube, a 6D cube, a 100D cube, and so on. And not just cubes. All shapes have higher dimensional counterparts. Theoretically, there are endless dimensions, and while we can't see any of them, we can describe them using mathematics. Come on. Ugh. Every time I update this operating system. Anyway, now, about all these dimensions existing, just take my word for it. You do not need to come to terms with the existence of these dimensions in order to appreciate the bonkers weirdness of what I'm about to tell you about the 8th dimension. So, in this movie, I want to tell you about a particular geometric shape. Actually, it's not so much a shape, it's really more a structure. An 8-dimensional lattice, known simply and mysteriously as E8. Now that I got my 8D glasses on, I'm gonna watch me some 8D TV. For some reason, this 8-dimensional thing, known as E8, appears to encode all of the particles and forces of our 3-dimensional reality. So, let's talk about what E8 actually is. And what it is actually pretty simple. For reals. Imagine circles, all of them the same size. We draw them on a piece of paper stacked in the densest possible way that one can stack circles of the same size. This happens to be called hexagonal packing, by the way. Now, let's put a little point in the center of every one of these circles. And now, let's get rid of the circles and leave only their center points. So now, we have something called a point space. This point space is one that represents the densest packing of 2-dimensional circles of the same size, right? Now, let's talk about the densest packing of 3D circles, or spheres. Again, all of them of the exact same size. P.S. We're totally pretending that these oranges are perfect spheres of the exact same size. So, the densest packing of 3D spheres is actually pretty intuitive to us. It's how we pack oranges in the supermarket. By the way, this is kind of weird, but it was only in 2014 that someone was finally able to prove mathematically that this packing of 3D spheres is actually the densest. Weird, right? It was like this big mysterious problem for years in mathematics that nobody was able to prove. Now let's add points in the centers of all of our spheres while they're in this dense arrangement. And again, let's get rid of all of the spheres and keep only the points that represent their centers. Okay, so now we're left with the point space representing the densest packing of 3-dimensional spheres. So far, so good, right? Y'all with me? Okay, so E8 is the point space representing the densest packing of 8D spheres. Strings, please. Now, many of you have heard of Albert Einstein's theory of relativity. It's a theory that describes, among other things, how gravity works and how it affects massive bodies, like planets. And many of you have also heard of quantum mechanics. It's a theory that describes very small things, like electrons. No one has ever been able to unify these two theories into what we colloquially call a theory of everything, or more technically, quantum gravity theory. But for years now, there has been a theory that has claimed to be a serious contender in unifying these theories. And you've probably heard of it. It's called string theory. Problem is, string theory has kind of failed. For years, it has been getting tons of funding and grants in academia, but it has never produced any successful predictions. And there are many physicists out there who think that the time of string theory is over, and that E8 may play a more serious role in an eventual theory of everything.
So string theory definitely applies to paragliding. Not sure much else.
What do you got against string theory?
What don't I have against string theory? My name is Garrett Lisi, and I live in Maui because why would I live anywhere else? I was the person who first discovered a match between particle physics and E8. And when I first discovered it, it was so incredibly exciting. I knew I was going to be working on this probably the rest of my life. I came to Maui because I got my PhD in theoretical physics, and I thought about going off to do a postdoc somewhere, but pretty much everywhere I looked wouldn't allow me to research what I wanted. So I decided to split off to Maui and be a surf bum and work on what I wanted here. In the 90s, string theory was the hot research topic that everybody was going for, and I had looked at string theory and I just thought it was kind of far-fetched. I thought they were making a lot of unjustified assumptions about the way the universe works. It wasn't a bad idea when it started. They just overpromised and underdelivered.
What did they promise?
Well, string theorists promised to figure out a simple, elegant description of fundamental physics using a few simple principles, and they utterly failed to do that. They kept piling on more and more complications until the theory just got ridiculous.
What would string theory people say about what you just said?
If they're honest, they'd agree with me. But you know, people get very attached to the ideas they're working on, and after a long enough time, it becomes hard to let them go and move on to other things. String theory has a lot of inertia because you have grants in place that support the projects that are being researched. And you have students working on string theory problems who have started their dissertations, which can last many years. That's one good thing about working on your own. If you just decide the approach you're taking is not going to produce results like you thought it was, you can just wipe the slate clean and work on something else. As a graduate student, I really fell in love with Einstein's theory of relativity, his description of gravity as curving space-time.
Okay, so super nutshell explanation of how gravity works according to Einstein's theory of relativity. Now, this is a big oversimplification, so science nerds, do not hate on me. Basically, the idea is that space is a kind of fabric, and objects, such as planets, sit on this fabric and make it sort of bend or curve so that other objects, like other planets, will fall toward it. Heavier objects cause a heavier curving of space, or a stronger gravitational pull, meaning objects fall towards them faster. So this is a very geometric description of gravity.
When I studied particle physics, it wasn't a geometric theory in the same way that gravity is described as curving space-time. So I wanted to understand a description of elementary particles that matched up with Einstein's theory of gravity. Because the universe is just one thing, right? So there has to be a unified description of this place where we are living. When you do fundamental mathematics, you invariably see these very elaborate, complicated, beautiful mathematical structures that come out. And it just so happens that some of these beautiful mathematical structures describe our physical universe. We know of these forces that exist in the universe, right? Gravity, electromagnetism, the weak force, the strong force, and we have this whole spectrum of elementary particles and properties.
So this is an idea that's been around for a long time, and I'm going to describe it using a hypothetical scenario. Imagine if we lived in a two-dimensional universe, a totally flat universe. All particles, atoms, people, buildings, all are totally flat, like a cartoon. Okay, so in this 2D universe, all particles, such as electrons, quarks, photons, would all be two-dimensional. So let's take one of these hypothetical two-dimensional photons, for example. The idea is that there is a circle attached to it in the third dimension, sort of above this 2D universe, in such a way that the photon is actually just a point on that circle, and that point appears in our 2D universe as a photon. We cannot see the entire circle popping out of 2D, just the point of the circle that touches our universe. This circle is called a fiber. The fiber represents how the photon moves through space and time. So a photon is represented by just this one circle, and other particles and forces are represented by different combinations of circles. The fundamental force, known as the weak force, for example, has 3 circles that twist around each other in certain ways. These groups of circles form what are called Lie groups. Okay. So that explanation assumed a hypothetical two-dimensional universe. But in our actual universe, which is in 3D, the fibers attached to our 3D space are in even higher dimensions.
So physically, we live in 3-dimensional space. And there are these other higher dimensional fibers attached to every point of our space. And as these fibers twist over our space in time, that appears in our space as particles propagating from one point to another. This is what all matter, all forces, this is what everything is. This description of particles is entirely geometric. All the forces we know of, they're coming about from the curvature of these fibers, the same way gravity is a curvature of space-time. And this has actually been known and standard in physics for over 70 years now.
So this idea was exciting for a few decades, but then people sort of forgot about it and started working on string theory. But string theory, as you guys know, didn't pan out so well. So Garrett took a big step backwards and tried to combine the theory of these circles with gravity. And some interesting things happened. So just like numbers, you can add Lie groups. Like you can literally add groups of circles into larger groups. So when Garrett added together the Lie groups representing each and every force and particle in nature that we know of, along with the Lie groups representing some theorized but not yet seen particles, such as the graviton, which is a theorized gravity particle, they all formed this one big Lie group. And I mean a really big Lie group, one that has been known about in mathematics for years. And you guys already know what it's called. It's called E8.
E8 is considered by many mathematicians to be the most beautiful structure in mathematics. And it just so happens that there's this correspondence between the particles we see in nature and this most beautiful mathematical structure ever discovered. And there are some discrepancies. We're not sure exactly how it will work or whether it will work at all, but there's enough of a matching between the known properties of elementary particles and the structure of this geometric mathematical object that it's very promising, very encouraging for describing physics.
So, to really simplify this, and again, science nerds, don't hate on me, I'm just trying to give you a simple visual. Imagine if behind every particle we see in our 3D world, there is this 8-dimension sort of E8 machine behind the scenes that turns and rotates. And when we view a particle in our world, we see it as an electron or quark or photon or any other thing according to what this E8 machine is doing over there in the 8th dimension and according to its orientation relative to our world. So all particles and forces and space-time itself can geometrically transform into one another according to the geometry of E8.
So are all particles the same somehow?
Yeah, they're all different fibers of this E8 Lie group.
Well, that's just weird.
Isn't that great?
So it's weird and mysterious that a point space in 8 dimensions is so somehow fundamentally related to our 3-dimensional reality, isn't it?
Yeah, that's weird. Yeah. I mean, it's wonderful and mysterious why mathematics works so well to describe our universe at all. Our physical laws, the fact that they're accessible to us, and that some fundamental bits of mathematics actually describe our physical world, that's really remarkable. Like we're living in a bit of mathematics that's come to life.
I'm not sure about whether
And
the empire has to be, but once you have the linear window,
This is a theory which is documented.
And then you go one step larger in the size of your tetrahedron, and then 10 steps larger, then 1,000,000 steps larger. All of the breakthroughs in physics have come from people willing to step outside the box and do something creative and radical. Hi, my name's Clea Irwin. I'm the director of quantum gravity research, working on a theory of everything called emergence theory. I've given up every other focus in my life. I quit my job as an executive years ago to focus on this every day with a team of physicists and mathematicians who work with me.
Yes.
What is reality? Is reality made of energy? And if so, what is energy? Is reality made of information? And if so, what kind of information? Is it binary, made of zeros and ones? Is the universe a binary computer?
Okay, so in Clee's theory, reality is at its most fundamental level a code, or a language, and this code relates deeply to E8. Clee envisions a substructure of space and time at the tiniest possible scale. You know how your TV screen is broken down into fundamental units called pixels? Well, emergence theory suggests a three-dimensional pixel of reality, a fundamental building block that everything is built from, the tetrahedron, which is a three-dimensional equilateral triangle. These tetrahedra combine with one another through various mathematical rules throughout all of space into a massive structure Klee calls the quasi-crystalline spin network. And this network isn't some random arbitrary idea. It comes directly from E8.
So now you have a conundrum, because you have this mathematical idea that reality relates to higher dimensions, and yet you're measuring or observing 3D. So the only solution that we can think of is quasi-crystals.
Quasi-crystals. That's a mouthful. Some people call them quasi-crystals. Okay, so let's talk about what a crystal is first. A crystal refers to a type of pattern, a periodic pattern. A checkerboard is an example of a two-dimensional periodic pattern where if you extend it infinitely, it'll just be the same pattern forever. You can also have three-dimensional crystal structures like this cubic lattice. Now, imagine projecting a three-dimensional cubic lattice to a two-dimensional surface. You create a shadow. This shadow also has a pattern, but it isn't periodic. It also isn't random. It's aperiodic, a quasi-crystal. A quasi-crystal in a certain dimension is a projection of a crystal in a higher dimension. Remember those points representing the densest packing of circles and spheres? Actually, those points are arranged in a crystalline order. Now, the E8 lattice is actually an 8-dimensional crystal, and Klee's group projects this E8 crystal from 8D to 4D to 3D at a specific irrational angle to form their theorized fundamental substructure of spacetime.
When I make an irrational projection of E8 down to a lower dimensional shadow of E8, something remarkable happens. The object becomes a language. That is, it becomes a finite set of geometric letters, rules on how you can arrange those letters, and freedom within those rules, which allows you to express or encode information. So, this three-dimensional quasi-crystal...
No, this is my line. So, this three-dimensional quasi-crystal is essentially a geometric code. A code composed of symbols which express meaning. And this meaning is reality itself.
String theory speculates on a number of hidden dimensions. And when we ask, well, why can't we measure these dimensions and observe them, then the answer is, well, because they're too small to see. In our approach, we never have to introduce the higher dimensions because we get the same information of the higher dimensional math encoded in the three-dimensional dynamic quasi-crystal language. Mathematically, one can recover the information of the E8 lattice that encodes unification physics from the lower dimensional quasi-crystal. To me, to be able to even have a 1 in a million shot at discovering the very keys to the fabric of reality is just fun. Like, what better treasure hunt could one have? I think that the world is getting crowded, and there's a lot of people not having fun because they're focused on getting enough water that's clean or food. And perhaps understanding the deepest secrets of nature at the smallest scales will be like having the keys to the kingdom. So imagine if we discovered the very fabric of reality in explicit detail, the very workings at the pixelated scale of reality. That should open up a treasure trove of new technologies, and perhaps even new philosophies relating to the strangeness of quantum mechanics that allow things that we couldn't imagine.
The road to knowledge is a long and winding one, filled with moments of glorious scientific discovery, but also ones of bitter disappointment. Whether or not Klee and Garrett's theories become accepted as mainstream quantum gravity theories, many physicists believe that reality is deeply related to higher dimensional objects. E8, perhaps as real as it is mysterious, appears to be a real contender on the road to discovering a theory of everything.
Hey, can you reward them for sitting through that whole explanation with like some 80s rock and roll? Do you remember last year when I did this science documentary, the What is Reality? I think I sent that to you. I can't really remember. But anyway, my most favorite part about that was this part about matrices, and there was this word in it that I wasn't quite sure on how to pronounce. It looked to me like eigenvalue. So, right, I mean, I think that's what you would think, eigenvalue. So I asked, is this how you pronounce it? And David, the director, said, yes, that is how you pronounce it. So I went out there and said, that's right, eigenvalue. And then apparently the internet went nuts when it came out, because apparently it's pronounced eigenvalue. That's how you're supposed to say it. And the director, don't bleep me, the director told me to say eigenvalue, and it's eigenvalue, and the whole internet just like caved in on my skull, and it's just kind of been awful, but like I get it, and I feel like you're the only one who understands these kind of things. It's just nice to get it off my chest, but it's just like, man, eigenvalue, eigenvalue, eigenvalue. It's not even like that.